Good morning, one and all. My name is A. Sai Siddharth. I am from ECE second year A section of roll number 24BQ180408. Going to present a seminar on power spectral density in probability theory and stochastic process. So the average power can be represented as Pxx is equal to limit t tends to infinity 1 by 2t integral over t e of x square dt. For a wide sense stationary random process, the expected value of E of x square of t is equal to autocorrelation without any lag. That is, average power is equal to Rxx of 0. Now we will see the relation of power spectrum density with the average power. So we know that autocorrelation is the autocorrelation is the inverse Fourier transform of power spectral density PLD. If we substitute tau is equal to 0, then the condition will become Rxx of 0 equal to 1 by 2 pi of power spectral density with respect to d omega. So this equation shows that the total average power of a WSS random process is equal to the area under power spectral density curve. So to prove this, we will consider a random process. Consider a wide sense stationary random process x of t. To find its Fourier transform, let the process be defined with a finite interval over t, that is, xt of t is a truncated signal of x of t for which minus t less than t less than. So the Fourier transform of the truncated signal xt of omega is equal to integral over t xt of t into e power minus j omega t. Now the average power over interval t is given by p of t is equal to 1 by 2t integral over t magnitude of truncated signal whole square dt. So we can, by using Parseval's theorem, we can relate that p of t equals to 1 by 2 pi integral minus infinity to infinity magnitude xt of xt of omega whole square by 2t d omega. So as when t tends to infinity, the term xt of omega represents power spectral density Sxx of omega. Thus the total average power is obtained by integrating power spectral density over all frequencies. So there are some important properties of power spectral density. The first property is power spectral density cannot be negative, or it should always be greater than 0. From the definition, the expected value of a non-negative function e of xt of omega mod whole square is always non-negative. So this is a sufficient proof to show that power spectral density is always positive or greater than 0. Sxx of omega is equal to minus infinity to infinity Rxx of tau into e power minus j omega tau d2, which is nothing but the Fourier transform of the autocorrelation function. So at 0 frequency or omega equal to 0, Sxx of 0 is equal to Rxx of tau d tau. Third property is that the power density spectrum of a real process x of t is an even function. Sxx of minus omega is equal to Sxx of omega when x of t is real. Consider a WSS real random process x of t, then sxx of omega is equal to minus infinity to infinity rxx of tau into e power minus j omega tau d tau, which is nothing but the Fourier transform of autocorrelation function. Also, sxx of minus omega is equal to integral minus infinity to infinity rxx of tau into e power j omega tau of tau e power j omega of tau, as this minus and minus omega becomes plus. Substitute tau is equal to minus tau, then the equation will become sxx of omega is equal to minus infinity to infinity rxx of minus tau into e power minus j omega tau d tau. So from the properties of autocorrelation we know that rxx of minus tau is nothing but rxx of tau, which is an even function. So sxx of minus omega will become minus infinity integral minus infinity to infinity rxx of tau into e power minus j omega tau d tau. Now, so this equation implies that sxx of minus omega is equal to sxx of omega. Fourth property. Fourth property is that power density spectrum is always a real function. Sxx of omega is always a real function. Sxx of omega is equal to limit t tends to infinity e of expectation of mod xt of omega whole square whole divided by 2t. Since the function mod xt of omega whole square is a real function, Sx of omega is always real. So this is the sufficient condition to prove that Sxx of omega is always a real function. If Sxx of omega is power spectral density of WSS random process x of t, then the time average of the mean square value of WSS random process equals to the area under the curve of power spectral density. This can be mathematically represented as 1 by 2 pi integral minus infinity to infinity Sxx of my omega d omega is equal to time average of expectation of x square of t, which is nothing but autocorrelation at zero lag. So to prove this, we'll take the autocorrelation function rxx of tau is equal to time average of expectation of x of t plus tau into x of t. This is equal to 1 by 2 pi integral minus infinity to infinity sxx of omega into e power j omega t d omega. So now we'll substitute tau is equal to 0. The above equation will become rxx of 0 is equal to average of expectation of x square of t, which is nothing but 1 by 2 pi integral minus infinity to infinity sxx of omega d omega. So this is nothing but the area under the power spectral density curve. So if x of t is a wide sense stationary random process with power spectral density sxx of omega, then the power spectral density of the derivative of x of t is equal to omega square times of the power spectral density sxx of omega, which is nothing but if sxx dot omega is equal to omega square times sxx of omega. So if this is the power spectral density of the derivative function of x of t, then this will be equal to omega square times of power spectral density of the original process x of t. This can be, so the mathematical proof is, so we'll take sxx of omega is equal to limit t tends to infinity expectation of mod xt of omega whole square by 2t. Now xt of omega is equal to integral minus t to t x of t into e power minus j omega t dt. Now we will differentiate with respect to t on both sides. So this is differentiation, and this will become dxt of omega by dt is equal to d by dt of minus t to t x of t into e power minus j omega t dt. Now we can see minus j omega into minus t to t x of t into e power minus j omega t dt. So this is nothing but the truncated signal xt of omega. So now we can prove that sxx dot of omega is equal to limit t tends to infinity e of expectation of xt of omega whole square whole divided by 2t. So from the above equation we can further express that limit t tends to infinity omega square e of mod x of t omega whole square whole divided by 2t. So we can finally express this equation as sxx dot or derivative function power spectral density is equal to omega square times of the power spectral density of the process x of t. Thank you.